Hello everybody. Thank you for coming for my talk. The title is Mad HTLC because HTLC is crazy cheap to attack. HTLCs are the basic building block in many cryptocurrency systems, and we know they are vulnerable to bribery attacks on Ethereum. In this work, we show they are actually vulnerable also on Bitcoin, and the attacks are cheaper and simpler than what we previously know. But we also propose a solution, Mad HTLC. So it's secure, incentive compatible, and you can just plug it in and it will work. This is a joint work with Matan, Alex, and Itay, and it's in the proceedings of Oakland 221, and you can also find it on archive. I'll start with some background to make sure we're all on the same page. And yeah. Okay, so we have the blockchain cryptocurrencies, which are systems that facilitate transactions of tokens among the users, and they use the blockchain as the main data structure. The main operators in the system are the miners. They include transactions in blocks, and they receive transaction fees for doing so. Miners are incentivized to choose which transactions they want to include, and we call these obviously they want to optimize to get the maximal reward from that, and we call these optimizations as MEV, okay, miner extractable value. The tokens are associated with contracts. These are predicates that are evaluated on transaction data. The predicate must evaluate to be positively evaluated, and then the transaction is valid. We say that a confirmed transaction, meaning a transaction that was inserted in a block, redeems an input contract. And please note that a contract can be redeemed only once. Hash time lock contracts, HTLC is sometimes referred to as hash time locked contracts, but let's go with this variation. Contracts established by two users. I'm going to refer to them as Ant-Man and Batman. They include a hash digest for some cryptographic hash function and a timeout T that is measured in blocks. As I said, they're the main building block for many cryptocurrency systems, the Lightning channel, Lightning network, atomic swaps, contingent payments, and so on. So how does the predicate of an HTLC look like? As follows. So we have Ant-Man that can get the tokens with a matching preimage. We said that we have a hash digest, so you need to provide a preimage for that hash digest, and then Ant-Man can get the tokens. Alternatively, Batman can get the tokens if he waits the timeout to elapse, okay, the timeout in blocks. We refer to this as the hash lock and the time lock, and this is why we call this an HTLC. So consider an HTLC initiated on block X. And consider the two transactions, one by Ant-Man solving the hash lock and one by Batman solving the time lock. So Batman's transaction can only be put in the blockchain starting at block X plus T, okay? Only after the timeout elapses, and only if the tokens hadn't been taken yet by Ant-Man. And note that the miners are those who pick which transaction is included and in which block. So when these systems that I mentioned use the HTLC, they make the following assumption. They say that if Ant-Man publishes the transaction with the preimage, then if he publishes it before the timeout elapses, then that transaction is indeed included in the blockchain. But there is a known issue here, right? Because the miners are those who pick which transaction is included. And these systems don't address this issue at all. Sorry. And specifically, they neglect the miners' incentives to pick transactions that offer them more fees. And we have this misalignment. We have an attack, an option for attack, right? So the attack is real simple. Batman can bribe the miners to exclude Ant-Man's transaction until the timeout elapses, and then take his transaction instead. So as a toy example, consider that Ant-Man's transactions offer a single token as fees. There's something wrong with my slides. I guess this is not the latest version. Never mind, sorry. So consider that the HTLC token, the HTLC contract holds 5 tokens, and Ant-Man's transaction offers 1 token as fees. So the intended scenario would have Ant-Man receiving 4 tokens after his transaction is confirmed, Batman would get nothing, and the miners would get a single token. However, if Batman decides to take an action and to offer a higher fee, say 2 tokens, then Ant-Man would get nothing because his transaction would not be put in the blockchain. Batman would get 3 tokens, which is more than 0, and the miners will get 2 tokens, which is more than 1. So this is clearly better for both Batman and the miners. Okay, so this attack is known, okay? It was discussed by Windsor et al. In a previous work from 2019. They suggested using an Ethereum smart contract to coordinate this attack. This contract is a bit elaborate, so it's only supported by the Ethereum opcodes, but not by Bitcoins. It also requires prior deployment, meaning it has some cost regardless if the attack succeeds or not. Okay, so you have to actually deploy the contract before the attack takes place. Meaning you pay before the attack takes place, so you might end up just paying for it and the attack failed. They analyzed the required cost for this attack, how much you would have to offer as a bribe, and they actually consider how much would you need to pay to a single miner to incentivize them to support this attack. And that amount depends on how all other miners behave. So if they all support the attack, then that cost is independent in the timeout. Okay. Alternatively, if they all oppose the attack, then that cost is exponential in the timeout. Okay, and this suggests that if you just increase the timeout, then you make the attack too expensive to execute. So this is like optimistic in a sense. But sadly, we show this is not true, and the attacks are actually simpler and cheaper and are independent in the timeout. And we also show they apply in Bitcoin as well. So let me show you. Our version, 2.0. Just use the transaction fee mechanism to offer the bribe. You don't have to coordinate through a smart contract. Simply offer a future transaction that offers more fees. Then you can actually bribe the miners to choose your bribe transaction. This makes it Bitcoin compatible. It means you don't have to have some prior deployment of a bribe contract. You simply offer the transaction, so you have no cost if the attack fails. To analyze this, we consider a game played by Ant-Man, Batman, and the miners. Okay, miners are part of the game. The game comprises rounds, which correspond to the creation of the T blocks. And we analyzed it using subgame perfect equilibrium. Okay, this is a solution concept that captures the ongoing decision-making that all parties make throughout the game. As an example for SP analysis, consider the game of tic-tac-toe. Okay, you know, Ixigul. And when you want to decide what you want to do in this game, you actually simulate all possible game extensions, and you choose the action that leads to the desired result. Okay, and subgame perfect equilibrium means that you're satisfied with your decision at every point of the game. Okay, so at every one of the subgames, you're happy with what you chose to do. This is subgame perfect equilibrium. The analysis technique uses backward induction, which means you play the game until the end, and then you recursively propagate the results back to the decision point. Our analysis shows that the required bribe is not affected by the timeout. Okay, so this means that you can't simply increase the timeout and make the attack too expensive. It doesn't matter. So this is a conceptual issue, not some poor parameter choice. We also show it's cheap, and we found multiple instances on the Bitcoin network where you could just pay $2 as a bribe and get over $26,000 in potential reward. I'll say that it's not exhibited today, probably due to poor MEV optimizations by the Bitcoin miners, but that's not something to rely on, right? We can just trust them not to optimize to make sure the system is secure. So one might say, okay, so let's let Ant-Man counter bribe, right? Batman bribe, so you can counter bribe and so forth. We actually consider that. And we show that the required counter bribe is linear in the secured amount. So going back to the previous example, the overhead would be something like 10,000 times more than what you originally intended to pay. You'd have to pay to make that your transaction secure. So this is not a solution, right? We can't rely on that. So we need something more systematic. And we have MAD HTLC. So what is MAD HTLC is our solution. And recall the problem with the original HTLC was that we neglected the miners. So let's not do that anymore, right? Let's consider them as part of the contract. Let's incentivize them to enforce the desired execution and to deter attacks. Quick overview of the remainder of this talk. I'm going to present MAD HTLC, its design, its security and incentive compatibility proofs. I'm going to talk about the implementation and some network deployments. And I'm going to present the Bitcoin MEV infrastructure we created. MAD HTLC relies on MAD, mutual assured destruction. This is a notion from game theory, stating that if one party attacks the other, they both end up losing. This is a deterrence mechanism. This is what prevents say, Russia during the Cold War to nuke the US because then they would retaliate and so forth. So the point is to deter attacks. And in mad HTLC, if either Ant-Man or Batman misbehaves, then they both end up losing. The design. The contract comprises two subcontracts. The first, we call it the deposit. This is like the main functionality, the HTLC-like functionality. The second is the collateral. They're separated only for Bitcoin compatibility because of the UTXO model, but on the Ethereum, they're consolidated to a single contract. We have an additional hash lock. So in total, time lock and two hash locks. The time lock is just like the original HTLC time lock. Hash lock 1 is just like the original HTLC hash lock. And hash lock 2 is an addition for this contract. And the predicate goes like this. So this is the deposit, the main functionality. Three options. Either Ant-Man gets the tokens by solving the first hash lock. Okay, this is just like in the original HTLC. Or Batman can get the tokens after the time lock, but now he also must solve the second hash lock. Okay, so the first two portions of Batman, the time lock is like the original HTLC. Hash lock 2 is an addition. Alternatively, anyone can get the tokens by solving the two hash locks. Okay, and when I say anyone, I actually mean any miner, because once the two preimages are revealed and say I published a transaction publishing the two preimages, anyone can publish a similar transaction and take the token themselves. So we expect miners to do that because they control what actually goes into the blockchain. So we create MEV opportunities to enforce the correct execution. The collateral, which is optional, has the same lock parameters, but simpler. So we have Batman and the time lock, or any miner after the time lock and the two hash locks. Okay? This is an optional, and I'll later show why you can use it. So let's prove this is secure, right? We need to show this is secure and compatible. The first step is to show or to define the desired interactions with such a contract. Specifically how you create it, how you initiate it on the blockchain, and how you redeem it. So we actually define how we want the parties to be able to interact with it. For example, we want that parties can redeem the hash lock only if they have the preimage, right? Makes sense. Or that miners initially do not have both preimages because then they can just take the money themselves. Okay, so we have this list of desired ways the parties can interact with the contract. Then we showed this is actually the only way to interact with it, okay? So we use the UC framework, we define an ideal functionality, we define a protocol that states how you create, initiate, and redeem the contract, and show the worlds are indistinguishable. This is a classic UC proof. I'll say that the protocol uses the hash function and the blockchain is an ideal functionalities. So we prove an indistinguishability between a hybrid world and the ideal world. Then, using the desired interactions that we defined, we're able to formalize a game played by Ant-Man, Batman, and the miners. Again, we analyze it using SPE and show it is incentive compatible, meaning no party gains by deviating. All parties behave as intended. I'll give you some intuition. So consider a case where only one of either Ant-Man or Batman tries to redeem the contract. This matches one of the red squares. So in that case, only one of the preimages is published. So the miners can't get the tokens themselves. Okay, so the respective party gets the tokens. However, if both of them try to get the tokens, then both preimages are revealed, and then the miners simply take the tokens themselves. Okay, so this is like one party misbehaved, and the miners punish both of them. As a last scenario, consider that if Ant-Man published his preimage, that means that Batman can't get the tokens anymore. Okay, you'll notice that once Ant-Man publishes the first preimage, Batman can't get the tokens anymore. So that might incentivize him to publish his preimage anyways because he might be spiteful. Okay, so this is where we have the collateral contract, because if he does so, he will lose the collateral tokens, and if he doesn't do that, he will get to keep them. Okay, so this is why we have the optional collateral contract only to prevent a spiteful Batman from misbehaving. Okay, let's move on to the implementations. So we implemented Med HTLC using both the script for Bitcoin and Solidity for Ethereum. The overhead for Bitcoin is a few dollars because the contract has a bit more opcodes, but that's it. On Ethereum, it's a bit more expensive because you have to initiate a new contract, which is very expensive on Ethereum. But we have an amortized version, which is way cheaper, so you can use that. I'll mention that the overhead is independent in the secured amount, okay? So the cost is not dependent on how much you have in the contract itself. It's just the transaction fees, sorry, which is way cheaper than what you would have to pay in a counter bribe, going back to the previous $26,000 Bitcoin contract example. Sorry. Let me also say that for the Lightning Network, the HTLCs only make it to the blockchain in case of a dispute. So this means that you wouldn't have to pay unless there is a dispute, and that isn't supposed to happen anyways. Well, in case both are acting as desired. We actually deployed the contracts on both the Bitcoin and the Ethereum networks. On Ethereum, some of our transactions were front-run, meaning someone offered a transaction that stole our money. This is expected. There's a lot of MEV on Ethereum. We actually expected that to happen. I was really happy someone stole my money. On Bitcoin, however, none of that happened. And we asked ourselves, why? Why wouldn't people take our money, right? We just basically offered free money, and no one took it. And the question is, the answer is that Bitcoin on MEV, well, isn't that developed yet? And we ask ourselves, why? Why wouldn't people optimize for that? Is it hard? Is it impossible? So we actually showed it's not the case by implementing a Bitcoin MEV infrastructure. So what we did, we took the popular Bitcoin Core client and we patched it to support MEV. We have two patches. The first is specific to the HTLC bribe attacks. So you'd have, you'd have a miner observing a bribe transaction and delaying Ant-Man's transaction until the time of the elapses, and then taking the Batman's transaction. This required 150 lines of code. We also have a more general patch that creates an MEV infrastructure. Essentially what it does, it exports all transaction data to an outer Python module where one can implement any logic of choice. And then it takes the data back inside and creates the block that you wanted. To conclude, HTLC is vulnerable. The bribe attacks apply to Bitcoin as well. They're cheap, they're profitable. They rely on MEV, which is easily implementable. And simply increasing the timeout is not the solution. We propose Med HTLC. It's secure, it's incentive compatible, minor overhead compared to the secured amounts. It's easily supported by the miners, and the source is available online. And thank you very much.
So we have time for a couple of questions. Is this a cap? Relying on proof of work? It doesn't depend on the timeout.
The question was whether the attack relies on proof of work, and the answer is no. It doesn't matter how the miners get to create the block, but essentially, since they pick what transactions are inside, it doesn't matter proof of work, proof of stake, proof of... Yes, so the required bribe actually depends, takes into account the probability that you will get to create the future block. So say you have 10% to create the block, I need to offer you a higher fee than that to make your expected profit greater than whatever. Okay, so let's say Ant-Man offers 1 token, so I'd offer 11 tokens as Batman for you with 10% to prefer my transaction, my future transaction. Okay, when you'll get to create a block, the relevant X plus T block, you'd have 10% to create the block, so I offer 11 tokens. That means your expected profit by waiting is greater. Does that make sense? Yes.
One way it looks like you're saying here, okay, put a little and get a great reward. And in a free market, many people would have done it, and then everything would collapse. So what am I missing?
I'm not sure what your what was the first part of the question.
With $2 bribe,
Yes.
get a 26,000 reward.
Okay. So
Many people, this is great opportunity.
the analysis relies on all miners looking for these optimizations and being rational. This is clearly not the case as of today in Bitcoin. Miners don't seem to optimize for this kind of optimization. They don't look for this kind of optimizations, but that can change. Okay, so, and obviously I'm not a miner. If I were, I would execute these attacks and many more. But yeah, you need actually all miners to be rational for this analysis to apply.
Okay, we'll take the rest offline.
Sure. Thank you.